In this lecture, we'll talk about the third law of thermodynamics. So third law of thermodynamics is concerned with the behavior of system in equilibrium when the temperature approaches 0 degrees or 0 Kelvin. So we know from the definition of entropy, so entropy is, or small change in entropy is dq over t, and if I integrate on both sides, then I get s minus s naught is equal to integral of dq t from some temperatures at 0 Kelvin to some other temperature. So if I write this in terms of s, then s would be 0 to t dqt plus s naught. Now this definition of entropy, or this expression of entropy, is incomplete without knowing this constant, okay, without the information of this constant, which is the entropy at absolute zero, because we are dealing with entropy from absolute zero to some higher temperature. So in order to know the absolute entropy of a system, we need to know entropy at absolute zero. Okay. So basically, third law of thermodynamics gives us way to get the information about entropy at absolute zero. So we will get this information from the third law of thermodynamics. Okay, it's from the postulates of Nernst. Okay. So up to this point we were dealing with delta S, change in entropy. So for delta S, we didn't need to worry about this entropy at absolute zero. But in some cases, particularly in chemistry, when we deal with Gibbs function during some kind of chemical change or chemical reaction, we need to know the absolute entropy. Okay, so to get, let's say, in this expression for dg, it's negative s dt plus p dv. So in order to get information about that, we need to know this. Okay, so that means to know about dg, we need to know about s. So that means delta s is not sufficient to determine dg, or change in Gibbs function. Now we know that a spontaneous process occurs. This is from the previous chapter. Or in order for a spontaneous process to occur, there must be decrease in Gibbs function. Okay, keeping the temperature and pressure constant. So a spontaneous process occurs in a system which is kept at constant pressure and temperature, or temperature and pressure, when the Gibbs function decreases. And from the definition of Gibbs function in terms of enthalpy, so Gibbs function is H minus Ts, and we also have this reciprocity relation that we see when we deal with the Maxwell's, when we derive the Maxwell's relations. So S is minus partial G partial T at constant pressure. So using that in the expression for Gibbs function, what we get, so we get so let's call this equation 1 and that equation 2. So using 2 in 1, we get G is equal to H minus and minus is plus T partial G partial T at constant P. Let's call that equation 3. Now if I want to know the change in Gibbs function while going from some initial state to final state, okay, if I go from initial state to final state, so I need to find delta G. So delta G would then be equal to delta H, and we consider that the process occurs at isothermal or a constant temperature, constant temperature. So this is isothermal process. In that case, this temperature would be constant, so you can keep that as it is, and this would be partial T, so taking the change in G at constant P. Okay, so that's 4. So here we can see that the change in enthalpy and the change in the Gibbs function will be equal when this term is 0, which is when the temperature goes to 0. So when temperature approaches 0, okay, and this constant pressure process. Okay, so if we plot the change in Gibbs function and change in enthalpy on a graph, so as temperature increases, the change in Gibbs function also increases, and as the temperature increases, the change in enthalpy goes down like that, goes towards the negative value. Or an alternate way to look at this graph is So we have delta T delta S is equal to delta H minus delta G. So that means if one goes up, the other needs to go down. So when we decrease the temperature, goes towards left, when we go towards left, there is increase in delta H. Okay, it becomes less and less negative, and this delta G decreases. Okay, it becomes less and less positive. So, and as the temperature approaches 0 here, delta G would be equal to delta H. Okay. So based on a couple of experiments that Nernst did, he postulated that when the temperature tends to 0, not only is delta G and not only are delta G and delta H equal, but their derivatives also would be equal at that point. Okay, so at that point, what Nernst found was here, when T approaches 0, this partial delta G partial T at constant P would be equal to partial H partial delta H over partial T would be 0. Okay, so that means the slope of this graph would be equal. So slope of that graph and slope of this graph would be more or less equal when the temperature approaches 0. Okay, so again, when the temperature approaches 0, delta G partial T at constant P would be equal to, when temperature approaches 0, partial delta H partial T partial T at constant P. So this is Nernst postulate. Okay. Now we can write this one as, so limit T goes to 0, partial delta G is G final minus G initial, partial T at constant pressure. So as T goes to 0, in the limit of T goes to 0, partial H2 minus H1 partial T at constant P. So basically you can write this as partial G2 partial T at constant P. Again, this is for at T approaches 0 minus partial G1 partial T at constant P is equal to partial H partial T minus partial H1 partial T, okay, at constant P. So here 1 again is initial state of the system, and 2 is the final state of the system. Okay, now we have this reciprocity relation that S is partial G partial T at constant P P. And all these things that we are doing is to get information about S. Okay, that's why we want to use this reciprocity relation, so that we can introduce S. We get the information about S. So that means so these are not only equal at t goes to 0, they are also 0. Okay, so here if you take the slope near the absolute 0 temperature, you see that the curve is more or less flat here. Okay, so that means here the slope is 0, so that means these are also equal to 0. So that means these are equal to 0. So so using this expression in this one, we can write this as S2 minus S1, okay, is equal to 0. Okay, and this is as t approaches 0. So this is the Nernst formulation of third law. Of the third law of thermodynamics. So according to this, basically all the reactions in chemistry, or chemical reactions, you can see, in a liquid or a solid, in some kind of thermal equilibrium, take place with no change in entropy, in the neighborhood of absolute 0 temperature. Okay. So when there is any kind of chemical reaction occurs near absolute 0, then change in entropy would be 0. There is no change in entropy. Okay, that's the Nernst Nernst formulation of third law, which makes sense because we know that in any system the entropy is measure of how disorderly the state is. Okay, and at absolutely 0 temperature there is no motion. Okay, no motion means the state is in perfectly ordered state. Okay, so that means if it is perfectly ordered, then there is no change in entropy, so the entropy change would be 0. And this is true for not only solid and liquid, but all the states, okay, that are in equilibrium when the process occurs near absolute 0. And in 1911, Planck extended this hypothesis, this Nernst hypothesis, by assuming that it holds for G1 and G2 separately. Okay. So, like we saw before, when temperature goes near 0, G would be equal to H and that's what the Planck proposed. Okay, so we saw before that in Nernst formulation, he found experimentally that delta G would be equal to delta H when the temperature goes to 0. Okay, but here Planck proposed that G itself is equal to delta H. G itself is equal to H. Okay, when the temperature is close to 0, or when the temperature is approaching to 0. So this is Nernst postulate, whereas this one is Planck's postulate, or Planck proposed that. And also when temperature approaches 0, partial G, partial T at constant P would be equal to partial H, partial T at constant P. Whereas in case of Nernst, he proposed this partial of delta G with respect to temperature at constant P is equal to partial of delta H at constant T, partial of H with respect to T at constant P. Okay, that would be 0. But here Planck proposed that the partial derivative of G and H are equal at constant pressure near 0 Kelvin. So let's look at the consequences of the postulates made by Planck. So let's introduce this new variable. Introduce where phi is defined as G minus H. So then we have G, we got this in the previous part, so G is H plus T partial G partial T at constant P. So then we can write G minus H as phi, so T, so partial G partial T at constant P minus phi is 0. Okay. So here we'll call this equation 7, this one 8, and this one 9. So then, because we already know that this thing is 0, so that means phi would also be 0. Okay. And then we also have this relation. So that one will also give us partial g minus h partial t at constant p would be 0. So that means partial phi partial t at constant p is 0. Okay, so that's equation 10. And please keep in mind that these are true when t approaches 0. So now again let's see this equation. So this one, so t partial g partial t at constant p minus phi is equal to 0. Okay, so that's from 9. Now let's add minus t partial h partial t at constant p to both sides of this equation. So when we do that, we get t partial g partial t at constant p minus phi plus minus, actually we're adding that, so minus t partial h partial t p is equal to, just adding that to both sides, so partial h partial t at constant p. So then we get t common, partial t, g minus h is phi partial h partial t at constant p. So t, I can divide both sides by t to get rid of t. So here I get partial t phi at constant p minus phi over t. It's dividing both sides by t. Negative partial h partial t at p at constant p. So we know from L'Hopital's rule, L'Hopital's rule, when this temperature goes to 0, in the limit of temperature goes to 0, phi over t would be equal to the derivative of phi with respect to temperature. Derivative of partial derivative of that with respect to temperature at constant p. Okay. So using that and this expression, we get, so these two would be same, so that means 0 is negative partial h partial t at constant p. So in the limit of t goes to 0, then partial h partial T at constant P is 0. Okay, let's call that equation 12. And so from the previous equation, so we have this relation from previous one. So we have in the limit t tends to 0 partial g, so this is the postulate of Planck, p is equal to limit t goes to 0 partial h partial t at constant p. So since this is 0, that means in the limit t goes to 0 partial g partial tp would also be 0. Okay, and we know from the reciprocity relation that partial g partial t at constant p is negative s, so that means this thing is negative s. So in limit t goes to 0, s would be 0. Okay, so this is the Planck's statement of third law. So in case of Nernst, he proposed that delta S would be 0. There is no change in entropy near the vicinity of absolute 0. But here, Planck showed that the entropy itself is 0, okay, at absolute 0. So this is Planck's statement of the third law. So here he showed that the entropy of a system in equilibrium is 0 at absolute 0. Okay, which again makes sense because entropy is measure of how orderly a state is, and at absolute 0 there's no motion of particles, there's no like thermal motion, so that means the system would be in a perfectly ordered state. That means the entropy would be 0. There's no any disorder. Okay, so that's all for this lecture. We'll continue this in our next lecture.